Yeah, so today we'll be talking about biological chemistry and this is our course outline. So we will discuss elemental composition of cells, atomic structure one, atomic structure two, then the rest. So for today's lesson for biological chemistry, we will start with the origin of elements. Yeah, the origin of elements. So on a normal circumstance or on a normal scenario, when you hear of the word origin, it means the source, origin, the source. So basically, we are coming to talk about the source of what elements, how the various elements came into an existence, how the various elements came into an existence. So the first thing we will consider in tackling the origin of elements is the Big Bang theory. The Big Bang theory. So we'll be looking at three main types of theory or three main types of events that helped or that led to the production of what elements. So the first one that we'll be talking about is the Big Bang theory. The Big Bang theory. So in the Big Bang theory, it says formation of hydrogen and helium after the explosion of a hotly dense ball of primordial matter. So this means hydrogen and helium were derived from the explosion of a hotly dense ball of primordial matter. Primordial matter is more or less like an existing matter, pre-existing matter. You get it? So something that was there already, and all of a sudden the thing just exploded. So after that explosion, then we had hydrogen and what? Helium. So hydrogen and helium were gotten from the Big Bang theory. So the Big Bang theory helped us to gain hydrogen and helium. So as time goes on, as we move on with our lesson, we will find out that the hydrogen and helium will also lead to other formation of other elements as well. So in the Big Bang theory, what you just have to note is that one, hydrogen and helium were derived from it, and the hydrogen and helium were gained after the explosion of a hotly dense ball of what? Primordial matter. And as I said earlier, a primordial matter um, can be defined as an a pre-existing what matter. Yeah. So it was because of the explosion of these primordial matters or the hotly dense ball of primordial matter that led to the formation of what? Um, Hydrogen and what? Helium. So basically, this is the um, normal concept or basic concept you have to get when we talk about primordial matter. And also, a primordial matter can also be defined as the matter that existed in the early universe, consisting of light elements like hydrogen and helium, formed shortly after the Big Bang. or the fundamental substances in various philosophical and religious traditions. So you can search more about um, the primordial matter to get more insights on what you are talking about. So, for example, if you are being asked, give some examples of primordial matter. The primordial matters, we have the one that existed from the early universe, and the one that existed or found on Earth. So we can talk about the primordial nuclei, um, coagulum, plasma, and the rest here. So that's it. So this is the first concept you have to get about um, the Big Bang Theory. So the Big Bang Theory, when you hear it, just have it in mind that for the Big Bang Theory helped us to gain hydrogen, helium, when or after the explosion of a hotly dense ball of what? The primordial matter. So the next concept for the Big Bang Theory says that gravitational forces brought together clouds of gases, or in brackets helium and hydrogen, that eventually collapsed into vast galaxies of billions of stars. So what basically this means is that um, see, according to the Big Bang Theory, the first thing that we've achieved is, or the first element we have had or we've gained is the hydrogen, helium. And based on that hydrogen, helium, based on that hydrogen, helium, we're able to get other elements, other elements through the collapsing of a vast galaxies of billions of stars. So this was um, as a result of the gravitational forces bringing hydrogen and helium as the clouds of gases together, and after bringing them together they collapsed, and their collapsation led to the production of billions of stars. So as we move on, we will see that these billions of stars, or these stars which were produced as a result of the gravitational forces bringing together the clouds of gases, specifically the hydrogen, helium, will help us to gain other elements. So the stars that are being produced here will be very useful. So whenever you hear about the Big Bang Theory, just keep it in mind that for the Big Bang Theory, it helped, or in that theory, is when that we had hydrogen, helium through the explosion of a hotly dense ball of primordial matter. And also in the Big Bang Theory, we gain billions of stars as a result of gravitational forces bringing together clouds of gases, specifically hydrogen and helium. So when you get this concept, it will be very easy for you to explain the Big Bang Theory in case you are being asked to do so. In case you are being asked to do so. So for the Big Bang Theory, it's just these concepts that you have to get it. And when we talk about gravitational force is the attractive force between any two objects with mass. The attractive force. So I have two objects. The objects, they have to have a mass, and the force between those two objects is what? Or the attractive force between those two objects is the what? Gravitational force. So it is because of that gravitational force that brought together, it is an attractive force. So it brought together hydrogen and helium. So here hydrogen and helium will definitely be our objects. So it brought together the hydrogen and helium as a form of clouds of gases. Then these clouds of gases collapsed, and this brought about the production of the stars. So that's all about the Big Bang Theory. So the next thing we will consider is the fusion reactions in stars. Fusion reactions in stars. So fusion reactions in stars is also known as the stellar hypothesis. The stellar hypothesis. So the moment you hear about the word fusion, fusion just means bringing together two things to form a new what object. So you are coming to look at how some elements were brought together to produce the other elements with the use of stars. And as we know earlier, we've been able to produce some billions of stars in the Big Bang Theory. So those stars that were produced will help us in the stellar hypothesis. The formation of other elements in the center of stars, high temperature and concentration of reactants are required. So in the stellar hypothesis, what's or the key things you have to note is that for the stellar hypothesis, the elements were formed in the center of the stars. And before the elements will be formed, we have some two factors you have to consider. One is the high temperature and the concentration of the reactants are required. So the reactant has to have high temperature and high concentration. So for stellar hypothesis, before the reactants or any two elements will be combined in the center of the star to produce other elements, those reactants they have to have high concentration and high temperature. So that's a factor or the factors concerning stellar hypothesis in the production of other elements in the center of the stars. So examples of fusion reactions include helium. So helium here is two. So we've combined two helium to produce a beryllium. And the other example is the helium and the beryllium are being combined together. So you can see their mass numbers there. Helium has 4, beryllium has 8. So when you combine them together, you will get 12. And the atomic number or the element with the mass number 12 is carbon. So after bringing together beryllium and helium, you will definitely get um, carbon, which has a mass number of 12. The same as helium plus carbon. Helium has a mass number of 4. Carbon has a mass number of 12. 12 plus 4, you get 16. And this will lead to the production of oxygen because oxygen has a mass number of what 16. So the fusion reactions, we are combining two elements together. Just get it. We are combining two elements together in the center of the star to get other elements. And when we are combining these two elements, so in this case, for the first example, you see we have two He, two hydrogens. So those two hydrogens will be the reactant. And the fusion reaction, the factor in it is that those that reactant that will be combined together to form a new product. Those reactants they have to have a high concentration and a high temperature. So looking at example two, helium He and beryllium Be, they are the reactants. They are the reactants in these reactions. So those two reactants they have to have a high temperature and a what? A high uh, concentration. Please do get it. Yeah. So iron, the largest atom formed in a nuclear fusion reaction. So just keep it in mind that in this nuclear fusion reaction, iron was the largest atom to be formed. But as time goes on, we will see that other large elements were being formed as well. So we will look at how these or those elements were also formed. But the largest that was formed firstly was iron. Others larger than iron formed from neutrons emanating from explosion of a star and captured uh, by the nuclei of iron atoms. So those elements which are far larger than iron, for them they were formed as a result of uh, neutrons. They were formed as a result of neutrons coming out from the explosion of a star, and then those neutrons which were coming out from the exploded stars, the neutrons were captured by the nuclei of the iron atoms. So after it being captured, then it automatically formed those larger elements. So that's the basic principle behind how the larger elements um larger than the iron were formed. So it is basically that they were formed as a result of neutrons coming out. Emanating means like coming out from the explosion of a star. So the neutrons were coming out from the exploded stars, and those neutrons which were coming out from the exploded stars were captured by nuclei, the iron nuclei, and after it captured it, it led to the formation of those larger elements. So elements with even mass numbers are produced by mainstream fusion reactions, while the odd mass numbers elements are produced by side stream reaction. So when you take the atom, you will get the atomic number and the mass number. So what we are just saying here is that for all the elements with an even mass number, all the elements with an even mass number, they were produced from a side from a mainstream reaction, from a mainstream reaction. So every element that has an even mass number was produced from a mainstream reaction. A mainstream reaction refers to the response, opinion or attitude held by majority. So the mainstream reaction, the type of reaction which is being accepted widely, So concerning mainstream reactions, most of the elements um with the even mass numbers are being produced from the mainstream reaction. So you can search more about the mainstream reaction or the mainstream fusion reaction. Then the odd mass numbers, elements with the odd mass numbers, they were produced from the side stream fusion reaction. The side stream fusion reaction. So that's basically about the mainstream reaction and the side stream reaction. So you can say that the mainstream reactions can be referred to as the primary reactions scientists are focused on for potential future clean energy production on Earth. So this can be a meaning that you can take for um, the mainstream fusion reaction. The mainstream fusion reaction. So just get it in mind that all the elements with odd mass numbers, they were produced from a side stream fusion reaction, and those with the even mass numbers, they were produced from the mainstream fusion reactions. So the next theory we are about to look at the artificial synthesis. So the meaning of synthesis is just simply production. Yeah. So if I want to synthesize something, I want to produce something. So you'll be looking at how other elements were produced artificially. How other elements were produced artificially. So the first one is a laboratory. So this artificial synthesis is the same as the what laboratory synthesis. So elements with atomic numbers beyond 92, that the transuranium element, have been synthesized in the laboratory by various fusion reactions. So all the elements beyond 92, all the elements beyond 92, these elements they were produced from the lab. So they were produced artificially. Example is a californium from the fusion of nuclei of carbon-12 with uranium-23. So californium is an example of um, an artificial synthesized element, and it was produced from the fusion of nuclei of carbon-12 with what uranium-238. So we've looked at three main theories. That's the Big Bang theory, the fusion reaction in stars, then artificial synthesis. So these were how elements were brought up. So these all constitute the origin of what element. So the next subtopic we'll be looking at is the element that constitute the cells. So we are coming to look at the various elements on the periodic table that we can find in ourselves, and why are they in ourselves, and why are others not in ourselves. So about 30 elements are recognized as essential to various living cells. So about 30 elements, over 100 plus elements on the periodic table, just 30 elements are just recognized as important to what the various living cells. So these 30 elements were selected based on some factors. They were selected based on some factors. So the first one is the properties of the biosphere. That's the composition of the earth and its atmosphere compared with human body. So the biosphere means when you talk about biosphere, just keep it in mind that it is the relationship between the earth and its atmosphere with the human body. You get it? Yeah. So for properties of biosphere, that was also a factor that was considered in choosing those 30 elements which have been essential to the body. So that's elements in earth. We have oxygen with 48.9%, iron with 18.8%, silicon with 14.0%, magnesium with 12.4%, carbon with 0.10%, similar to human body. So these elements found on Earth, the oxygen, the iron, the silicon, magnesium, carbon, they are all similar to our human body. That's it can be found in the what? The human body. And we have similar concentration of main ions in seawater and blood plasma like Cu2 plus, that's copper 2 plus, magnesium 2 plus, calcium 2 plus, Na 2 plus, and um, potassium 2 plus. So these all ions, all of these ions, they can be found in the seawater and our blood plasma as well, which is very essential to what? The human body. So please take note of the elements. It is very examinable. Can be given that oxygen has a percentage of fats in the or on earth or in the earth. So in an exam question, there can be a table due for you. The elements will be listed and you are being supposed to write their what percentages in there. So the next thing we will talk about is the chemical democracy. So almost every group of the periodic table has its representative in living cells. So all the groups on the periodic table, with the exception of the transition metals, with the exception of the transition metals, we have 8 groups. So when the transition metals are being added, we have about 18 groups also on the periodic table. And all of these groups, they have their representative element. They have elements that represent them in the living cell. So for example, we have our president. The president have many ministers and member of parliament who represent him in the various constituencies and various communities as well. That's the same thing for the element as well. So for the groups, they have each group has an element that can be found in the cells. 15 out of the 18 groups. So yeah, there are 18 groups when the transition metals are being added. There are 18 groups, but without the transition metals, we have 8 groups, as we learned in our JHS, SHS. Yeah. So 15 out of the 18 groups on the periodic table are found in cells. 15 out of the 80 groups on the periodic table are found in cells, except F block elements. So F block elements are elements which have their last valence electron. So for F block elements, they have their last or they have their valence electrons on the F orbital. Yeah, on the F orbital. So except these F block elements, that's the lanthanides and the actinides. So on the periodic table, the lanthanides and the actinides, they can be found below, yeah, down the periodic table. So except these F block elements, they are not found in the cells. All the other blocks, SPD, have their representatives in the cell. So SPD, the S orbital, the P orbital, and D orbital blocks, all of them, they have elements that can be found in the cells. The S block is found on the left hand side of the periodic table. The P is found on the right hand side, and the D is found in the middle. That's the transition metals. Yeah. Major or bulk elements like carbon, hydrogen, oxygen, nitrogen, phosphorus, and sulfur. So the various elements we have on the periodic table, we have some elements that are the major. Major means they are hugely demanded. They are hugely needed. They help us in our daily lives. They are used always. Yeah, that are the major element. And we have what? Minor element. To the major element, you have carbon, hydrogen, oxygen, nitrogen, phosphorus, and what? Sulfur, which constitute over 99% of the mass of most cells. So when you take the cell, these elements are very common in it, and they are present in organic compounds of cells. The minor elements include manganese, iron, cobalt, and nickel. They are present primarily in fluids that bathe the cells. So the features of these major elements are that firstly, the major elements, they are mostly p block elements. So when you take the major elements, they can be found mostly at the p block. Yeah, they are able to form covalent bonds. They are non-metals. They have smaller atomic sizes and numbers as well, and they are neither too reactive or not inert, but they are unreactive. So for these major elements, for them, they are not too reactive. They can't react that quickly, and also they are not inert as well. Inert means they they are not elements that cannot react with other elements. So they are intermediate. Yeah, but generally they are unreactive as well. Exclusion of some elements in cells. Why were some of the elements not being excluded? Or why were some of the elements excluded in the cells? So the first one is artificial nature. So elements with atomic numbers above 92 and 3 below, such as the technetium, astatine, francium, are artificially or all artificially made. So all the elements, if an element is artificially made, definitely it can be found in the cells, because the cells are naturally made. So this is why some of the elements, specifically atomic numbers with um or atomic numbers above 92 and 3 below, were excluded in a cell. The second one is the innate nature of the elements. So elements such as helium, neon, argon, krypton, xenon. So they are very scarce elements like actinides and lactinides as well. So these elements too were excluded as a result of their innate nature. They are not reactive. Yes. And the toxic nature of elements, lead, mercury, beryllium, they are very toxic to some parts of the cells. For example, lead causes anemia by inhibiting His and testis. Mercury, liver, kidney, brain damage. So when mercury gets into your body, it can lead to liver, kidney, and brain damage. And beryllium, they interfere with many functions of magnesium. So these were the reason why some elements like these were also not included in the cells. And the last one is the radioactive nature of the element. So radioactive nature, we'll be talking about uranium which give off radiation that could harm cells. So definitely uranium cannot be included in a cell because it gives off radiation. It's very harmful to the cells. Even though the radioactive elements are not essential in a cell, they can sometimes provide valuable qualities of life to the cell. Example, platinum complex is an anti-cancer drug. So we know that um, the radioactive element, they are not good to the cells or they are harmful to the cell, but sometimes some of them, they are helpful to the cells. Like for example, is the platinum complex, which serves as an anti-cancer drug. Unique properties of carbon for several compound formation. So for carbon, the reason why carbon is being included in every compound formation is that one, it has an ideal size. Carbon is not that huge, not that big, and also it is not that small. Two, it has the power of catenation. That is, it has the ability to form bonds with itself, straight chains, branches, and rings. It has so also carbon can form multiple bonds either with itself or other elements. And also it has the total valency. The total valency meaning that for carbon you have to have four electrons in the valence shells. You have to have four electrons in forming the compounds. So our next topic will be the structure and properties of what matter.